All right, so it's been a while since we learned this, but these images should remind you that we have learned how to find the prime factorization. So when we learned section 3.1, you guys were using the product puzzle and you were trying to find strings of factors, and then you filled out this table with all of the strings that you found, and in the end you were trying to find the longest string that you could possibly find, and the string had to multiply to make 840. So that was our goal, find a really long string that makes 840. So when all was said and done, and you guys finished that activity, we found a string that was 2 times 2 times 2 times 3 times 5 times 7. I hope that sounds familiar. It's been a while since we've done this, but that was the task. Take 840, break it up into a really long string. The way that you guys did that was you probably took your strings that were 2 or 3 long, and you started figuring out ways to break them up longer so that the strings were 4 and 5 and eventually 6, and then you were done. So once we got to this point, we established in class that this was the longest string. There is no longer string that could create 840. That was sort of the punchline of section 3.1. There is no string longer than this. You can't have a string with 7 factors, you can't have a string with 8 factors. And the reason we finally agreed to was that because all of these numbers are prime numbers, and if they're prime numbers, we can't break them up further. 2 is a prime number, 3 is a prime number. We can't break this into any smaller pieces. We could break it into 3 times 1, but 1's not a prime number, and that's kind of cheating anyway, because then we could make super long strings that don't do us any good. So we also agreed that the number 1 is cheating, it's not prime, it doesn't help us. This is the longest string. So in conclusion, you found the longest string when you take a number like 840 and you crush it up until you can't crush it anymore into all prime numbers. And you're supposed to put the prime numbers in ascending order. So we've already learned all of this, but what we're going to do next is talk about more efficient strategies so that you can take a number like 840 and get this string quicker so that we don't have to go through this whole process of building a table. Okay, so instead of doing 840, we're going to choose a smaller number, so 36. So the goal here is we're going to find the prime factorization of 36, and I'm going to show you what's a common wrong way to do it, and then I'm also going to show you a couple different ways to do it the right way. The method I'm going to show you is called the tree method. So this isn't the only method to find the prime factorization, but I think it's the fastest and it's the one that we're going to practice today. So I'd like you to try it out and see if you like it. The reason we call it the tree method is because if you flip it upside down, it looks a little bit like a tree where it branches out. Okay, so what we're going to do is we're going to split up 36. So we know that 2 times 18 is 36, so a common wrong way would be to put that 36 can be broken up into 18 and 18. Now, while it's true that 18 plus 18 does create 36, this is all about multiplication, so what we should do instead is 18 and a 2. And the idea is that these are factors, and factors multiply together, so 18 times 2 is what gives us 36. Otherwise, what we're really saying here is 18 times 18, which is some gigantic number, it's not 36. So don't think of this as addition. What we're doing is we're taking 36 and we're kind of smashing it on the head and trying to break up this composite number into smaller pieces. We're crushing 36 until the pieces get smaller and smaller and smaller. So at this point, 2 is a prime number and we can't smash it anymore. So we might want to circle it. That means we're done. 2 is prime. The 18, we could still break that apart. We could break it into 3 and 6. We could break it into 2 and 9. Doesn't really matter. Let's just do 2 and 9. At this point, 2 is prime, but 9 is not, so don't circle it. Can't circle it unless it's a prime number. And then 9 can be broken into 3 times 3. Remember, we should be able to multiply these together to create the number above it. And since 3 is prime and 3 is prime, we're done. So we found all of the factors that make 36. 2, 2, 3, and 3 multiplied together makes 36. So we're not totally finished because we need to finish writing out our answer. It's 2 times 2 times 3 times 3. Now, of course, some students might not break this into 18 and 2. They might see this as a 4 and a 9, because 4 times 9 equals 36. So the question is, if I start with a different choice on how I'm breaking up 36, will I still get the same string of numbers? Or will I get some different numbers? So look at it. Do you think I'll get the same string of numbers if I break 36 into 4 and 9? Let's try it out. So 4 becomes a 2 and a 2, 9 becomes a 3 and a 3. They're prime, we're done. Remember, we don't circle the 4, don't circle the 9. We can only circle them when they're prime. Composite numbers need to be broken and not circled. And sure enough, we got the exact same string. So if I chose to divide this into 18 and 2, I ended up with a 2, a 2, a 3, and a 3. If I decided to break 36 into 4 and 9, that was my initial split, I still got 2 and 2 and 3 and 3. This is the prime factorization of 36. This is the answer. There's no string longer than this because this string has all prime numbers. There's nothing more I can break up. And some students might take 36 and break it into 6 and 6. And if I break 36 into 6 and 6, each of those 6's has a 2 and a 3 in it, because 6 is a 2 times a 3. So we still get the same string, even if I did 6 times 6, or 4 times 9, or 18 times 2. And we could even try breaking 36 into 3 and 12. Will that still give us 2 times 2 times 3 times 3? Well, we have one of the 3's there. Is 12 made up of 2 times 2 times 3? Yes, it is. So, moral of the story, no matter how you break it up, you will always get the same string as long as you are not making any arithmetic mistakes and every composite number gets crushed down into its smallest pieces until they're prime. We don't add in any ones because one's not a prime number. We put them from smallest to greatest order. That's how you do the tree method.
All right, now that we've seen a few examples and what to do, we're going to practice. So take a few minutes. We have a easy, medium, and hard example. Complete as many as you can. And pause the video and we will show you the answers in a bit. All right, now that you've had some time to practice some of these, let's take a look at 72. Now, a lot of you may have broken it up into 2 and 36. But sometimes there's faster ways. So I'm going to start with 8 and 9. Now, I'm not going to circle any of these because they still can be made up by other parts, so I have to keep going. So I know that 8 can be broken up into 2 and 4, and 2 is prime, so I'm going to circle it. 9 can be broken up into 3 and 3. Those are both prime, so I can go ahead and circle those. 4, I need to keep working. And now I have the longest string of factors. 2 times 2 times 2 times 3 times 3. Now, do you think there's another way we could write this? You could also write this 2 to the third power times 3 to the second power. All right, that's 72. Now let's take a look at our medium example.
500, let's break it up. We have a 5 and a 100. 5 is prime, 100 is composite. From here we can do 2 and 50. 2 is prime. This is 5 and 10. Every time I do this, I'm circling the prime numbers. I'm not circling the composite numbers until we've taken 500 and crushed it as much as we can into little teeny tiny prime numbers. So we have a 5, a 2, 5, a 2, and 5. We could write that in expanded form. 2 times 2 times, how many 5s? 1, 2, 3. Or, as Mr. Long just showed us, we can also rewrite it in exponent form. Since there's 3 of the 5s, we've all learned exponents, you could write it. The little 3 means that I'm doing 5 times 5 over and over and over, 5 times 5 times 5, and I have 2 2's. Both of these forms are acceptable. This is expanded, this is exponents. Same thing here. This one's a little bit longer, so I'll have a few more steps. I have 5 and 1,000. I have 2 and 500. I have 5 and 100. 2 and 50. 5, 10, and 2 and 5. So that's a lot of steps, but every single step was pretty easy. I'm just dividing by 5 or I'm dividing by 2. I could have chosen a different way to start, but then when I'm done, I circle my prime numbers. And I have 1, 2, 3 2's. And I have 1, 2, 3, 4 5's. I could write that in expanded form, but there it is in exponent form. And let's just compare real quick how the blue one is bigger than the green one. I have, how many 2's do I have here? I have 2 2's and here I have 3. So I have more 2's on the right. I also have more 5's on the right. So it looks like I have an additional 2 and an additional 5. So this number is bigger, and it has a 2 and a 5 that this number doesn't have. They both have 2's and 5's, but this one has one more 2 and one more 5. And compare the original numbers. This one's 10 times bigger. I hope you can see that the connection is there. The extra 2 and the extra 5 makes a 10, which is why 500 times the extra 2 and the extra 5 gives us 500. So looking at the strings of numbers kind of helps us to see relationships that we might not always see.
And here we go for our final example. Let's take a look at 81. Pause the video and let's see if you can do it 2 different ways. So go ahead and pause. Welcome back. 81 is a little bit special because we can't divide it by 2. And sometimes when we can't divide a number by 2, we can get stuck. So if I was trying to break it up by 2, no number is evenly going to be multiplied to get 81. So I need to try other numbers. I can try 3. Oh, 3 does go into 81 27 times. Now I see a prime number, so I'm going to go ahead and circle it, but I need to break down 27 again. And 3 also goes into 27 9 times. 9 can be broken up until 3 and 3. So my factor string would look like this, or it could be rewritten in exponential form as 3 to the 4 because we have 4 3's. All right, so a second way you could have done this, looking, if we're not going to use 3 and we can't use 2, we could try 4, 5, 6, 7, 8, 9. 9 goes into it, so 9 times 9, and we can break those up into 3 and 3. And those are all prime, so we can go ahead and circle it. So again, we've used a different method. We started with a different pair, but we're going to get the same result in the end.
So I think we're done teaching you the tree method. And remember, the tree method can take any big number and breaks it down into its little teeny tiny prime numbers. So just to make sure that we're clear though, I'm going to pull the screen shade down and show you 5 possible answers for 840. So 840, we already know that it's a 2 and a 2 and a 2 and a 3 and a 5 and a 7. So I'm going to pull the screen shade down and you have to ask yourself, are these strings written in prime factorization form? Before I pull the string down, I'll go ahead and promise you all of the strings do multiply together to make 840. So if you put all 5 as the correct answer, that would make some sense because they all do multiply together to make 840, but are they written in the right form? That's the question. So 840. So take a look at A and ask yourself, is that string, which does equal 840 if I multiply it together, written in prime factorization form? The next string is right here, 2 times 3 times 2 times 2 times 5 times 7. The third string, 2 cubed, which is also, you can also say 2 to the third power times 5 times 7. Here we have a string that says 2 times 2 times 2 times 3 times 5 times 7. And the final string says 1 times 2 times 2 times 2 times 3 times 5 times 7. So once you've decided which ones are in the right form, you can maybe copy these down in your notes and put checks or X's. Make sure you go back and study this before the AOL. So go ahead and pause the video, write this down, take notes, make up your mind, then unpause and I'll tell you the answers. Okay, so we've unpaused and I hope that you agree with me that the D is correct. 2, 2, 2, 3, 5, 7 is the exact same string I gave you before. I hope you also noticed that C is perfectly fine. It's written in exponent form, not expanded form, and C and D are correct. So on the AOL, if you put your answers in expanded form or exponential form, you'll be okay. I hope you noticed that E is wrong because it has a number that's not a prime number. 1 is not prime, and if you have any 1s, then it's not written in prime factorization form. This one, B, is written in all prime numbers, but we're supposed to go from lowest to greatest. So just make sure that you switch the 3 over here and then you'll be okay. So this one's I don't know if it's right or wrong, but it's definitely not as good as it could be, so don't do that. Try not to do B. But A is definitely wrong because it's a perfectly good string. There's nothing wrong with it, but it's not in prime factorization form. So this is a string of numbers. It does equal 840, but if the instructions want prime factorization form, the whole point is we have to take that little 4 and keep crushing them until we only have prime numbers. So that's it for prime factorization.